In previous video, we tried to store minus 13 into our memory, a negative number into our memory, so to say. We came up with a solution that we are going to use a bit to identify the sign of a number, whether it's a positive or negative. That's good, that's very good solution. We ended up sacrificing one bit to store that particular value. In unsigned, we had 0 to 255 range for 8-bit number. For exact same 8-bit number, we have minus 127 to positive 127. Correct, the range is changing. Why? Because the leftmost bit, we are going to use it to store whether number is going to be a positive or whether number is going to be negative. Then we look at the possible combinations and we realize that we have two different values for 0, a positive 0 and a negative 0. And that creates a huge problem in arithmetic and very difficult to handle as well. That's why they came up with something called as 2's complement to store negative numbers. Now what is this 2's complement and how did we arrive at this? First we need to focus what was the problem. The problem was you have two different zeros, but we need to identify positive and negative numbers, right? So you need a bit to identify that. So this solution is good. This logic till here is good, that we need to store sign information into a bit. That is great. You cannot store in between somewhere, that will just conflict with the value that you have. You cannot just store on the right hand side, because again we start storing the value from right hand side, so we don't want the sign to go there. That's why we are using the leftmost bit to store the sign. That is great. Storing like this is actually creating a huge problem of positive and negative 0. We need a new solution that has easy storage, easy arithmetic, easy addition and subtraction and all the other operations. Also, one more thing I would like to highlight. Try to add positive 0 to negative 0. Look at this. You try to add these two numbers, you will get 1 0 0 0 0 0 0 0. You get negative 0. It's not just about the storage. This is the point I want to highlight. It's not just about the storage. It is actually causing a huge problem. And that problem is all arithmetic values are changing. Nothing is working as expected. So we need a way to store this value, these negative values into memory. We understand that we need to have a bit, a separate reserved bit to identify a positive number and negative number. That is good. We are just going to use this bit to identify the positive number and negative number, no problem there. So what is the solution that we have? So let's say you want to store some negative number. Let's say you want to store negative 5. So what we are going to do, you want to store negative 5 into the memory. First what you do, you write 1. Why? Because this 1 represents that value is going to be negative. This is the sign bit. Then you have 7 positions, right? Actually you have 8-bit number, so 8 positions, but the last one is already being used to identify the sign. Okay. Now what you do, this is the normal 5. You invert all the bits. You invert all the bits and you add 1 to it. Now this might look pretty random solution, right? We are inverting all the bits and then we are adding 1. And why are we doing this? Why are we doing all of this? See, 5 is nothing but 0, 1, 0, 1. Correct? Negative 5 is what we need to figure out. But if you add 5 and negative 5, you should get value as 0, so that your arithmetic will work properly. Now if you want to get this value 0, the only way is that an overflow. That means you need to add this particular number, positive 5, to some number that will set all the bits to 0. The only bit that is going to be 1 will be outside of 32-bit range. Here I am just using 4 bits, but actually this 5 will be stored using 32 bits, right? So you need to store this minus 5 in such a way that once you add 5 to minus 5, you get all the values 0 here and you get one value outside of 32-bit range. So your computer will definitely discard this value. Why? Because the range for int should be 32. Here we are just taking 4-bit as an example because I am lazy to write all 32 bits. So you want all the zeros. Okay, fine. So what you can do, if you just flip all the bits, it's called as 1's complement. And if you add this 1's complement into the original number 5, you get all 1's. This is called as 1's complement, reverting the bit. So why did we revert all the bit? So that we can get 1 everywhere. So if you add 1 to it, what will happen? Well, you get all the values 0 and you will have extra 1 as a carry. Now this will be ignored because it goes out of the range of 32-bit. Remember, I am just taking the example by writing 4-bit, but you will actually have this 32-bit number. So this carry will be at 33rd position and it will be actually discarded. So the value you will get finally is just going to be 0. But we don't want to add 1 here, so we are just going to add it 1 here. So 1's complement is nothing but inverting all the bits. 2's complement is adding 1 into 1's complement. And in this way, we managed to figure out how we are going to store negative numbers into memory. First, what we did, we reverted all of them so that if you add, you get all the ones. Then you add 1 to it, you get all the zeros, an extra carry which will be discarded by computer because it goes out of the range. You cannot add 1 to this particular answer, right? So you need to add this one in here itself at 1's complement. So that's what we have written here. First, you take the value, which is this value. Then you invert all the bits. Then you add 1 to this. So this value is going to be minus 5 now. I hope that you understand how did we arrive at these particular 3 steps, exactly these 3 steps to store negative values into memory. It's all about the arithmetic. We want our arithmetic to work perfectly. So first we did 1's complement, we managed to get all the ones. But we don't want the ones, right? We want all the zeros. So we added 1 here. By adding 1, you got all the zeros and 1 carry. This 1 carry will be discarded because it will be out of the range. Now thing is you cannot add 1 into the solution. So that's why you need to add 1 here itself while storing minus 5. So first you take the value of 5. Then you take 1's complement, that is invert all the bits. Then you add value 1 into it. And that's the exact 3 steps we are going to follow to store any negative number into the memory. 0 and 1, definitely we are going to use it to identify whether number is positive or not. For example, look at this. You have 1 here. That represents that this number is going to be a negative number. So value you have right here. How exactly are you going to get the value? You will follow the reverse process. Here you added 1, you will subtract 1. So you get something like this. Now you are going to invert all the bits. Now you get something like this. So now you have the 5. Now in original number you had 1, right? This represents that this number is stored in 2's complement and this 1 means that this number is going to be negative. So 5 is a value, sign will be minus. So this number is going to store minus 5. You get my point? We are just doing the revert operation to get the value of this. 1 tells us that this is a 2's complement, that means this number is going to be a negative number. So we followed the exact reverse approach. We subtracted 1 from it and then we inverted all the bits. That's how we got the value. And we know the sign by looking at this particular bit. That's what I have written here. How do I know that this number is going to be minus 5? Simple as that. Here we have 1. That means the number is going to be negative. Okay, what about the magnitude or the value? Well, we follow the exact reverse process. We subtract 1 from it. Now you have something like this. Then we invert all the bits. Now you have 5. 5 is going to be a magnitude or the value. Negative is just going to be the sign. And we got this negative value from the leftmost bit is 1. That's why we get this negative sign here.